All right, it's 8 o'clock and we have a nicely busy house, so we'll start. As I said, my name is Alex Lockwood. I'm replacing Frank Summers this evening. Not replacing, trying to emulate his magnificence. And I'm just here to host your evening. The real star of the show is Dr. Trisha Ashley. Just a couple of announcements. As I mentioned, if you're interested in going across the street to the Johns Hopkins Observatory and looking through their telescope, please meet after the talk up here at the podium. We have a couple of upcoming public lecture series. The public lecture series for September is on September 3rd. The topic is the Astronomers Toolkit, and the speaker is another outreach scientist named Dr. Brandon Lawton. Yay, Brandon. And then on October, the October public lecture is on October 1st, and the title is Black Holes and Gravitational Waves, which is very cool. And the speaker is from Johns Hopkins. His name is Emanuele Berti. I may have butchered that, but those are the upcoming talks. They're also available online, as is this recording after tonight. So with that, I would like to introduce tonight's speaker. Dr. Trisha Ashley got her bachelor's degree in physics and astronomy from Bryn Mawr College in 2008. In 2014, she received her PhD in physics from Florida International University. For her PhD dissertation, she studied star formation in blue compact dwarf galaxies as part of the research team Little Things. She has since worked on understanding the gas content in isolated early-type galaxies as a postdoc at NASA Ames, and she's currently working as a postdoc at the Space Telescope Science Institute with Andy Fox. Here at Space Telescope, she studies the Fermi bubbles and gas flows into and from and around the Milky Way. She also spends time as an organizer of Astronomy on Tap Baltimore, which I'm sure she'll be happy to answer questions about, an outreach program that brings scientists to bars in Baltimore to give fun and exciting talks about space. So please join me in a round of applause. Welcome, Dr. Ashley.
Okay, can you hear me? Good. Okay, that was a great introduction to my talk because it actually, now I can skip a few lines of my talk. So today I'm going to talk to you about dwarf galaxies. But first, as mentioned earlier, I actually wanted to tell you where I got my passion for dwarf galaxies, and that was during my dissertation, because as mentioned, I did my dissertation work on dwarf galaxies. So this is a picture of me getting my PhD. This is one of my official photos. Yes, very nice. And so I got my PhD because I did that work on dwarf galaxies. But I want to take a minute to analyze this photo because I'm a scientist.
That's Sherlock Holmes' pipe?
No, but very close. So this picture, I really believe, is a graduation photo level expert. And the reason I believe that is because, one, you got your monocle. Two, you have your pipe. Three, most of you may have missed it, but you have your flask strapped to your leg, filled with coffee, of course. And then finally, you have your facsimile degree because of Real Things in the Mail. So, as mentioned, I got my PhD on this work, and I've been interested in it ever since, and I continue to work on it on the side. But before I introduce to you a dwarf galaxy, I want to first introduce to you your own galaxy that you live in. And that is the Milky Way. So this is a beautiful picture taken of the night sky. And if you go out into a very dark place where the nearest city is tens of miles away and look up at the sky, you might see something like this. Now, it won't be this beautiful in color. It'll be mostly gray and white, but it's the same idea. We're going down the middle of this image, you have the Milky Way disk. So this is a galaxy that you all live in. And you can see it yourselves if you do go out to these very dark sky places. Now, if you take a bunch of images of the Milky Way from Earth and put them together, you can get an image like this, where most of the light is in this thin disk here. And that's the disk, the main disk of our galaxy, the Milky Way. So it's very thin. And most of that light is coming from stars in our galaxy. And so our galaxy is made up of stars, dust, gas, and dark matter, all of those things put together. And it's this little island of all of those things. So that's why I called dwarf galaxies islands of stars. Now, it looks very thin in this picture. Oops. Ah. We'll go back. Hold on, there it is. It looks very thin in this picture. That's because the main disk of our galaxy is quite thin. But that's only our view from the Earth. What does it look like when we leave the Earth and leave the galaxy and look back at it? Well, we can't actually do that because we don't have the technology to go that fast. But with the data that we've collected from the Milky Way, we can actually have an artist put together a picture of what we think it looks like if we were to leave the galaxy and go look at it from above. So this is what we think it might look like. Where you're here, about halfway between the center of the galaxy and the outer edge. And we do want to be there. We don't want to be too close to the center because too much is going on there. It would be very disastrous for us as a population. But you have a couple of features here that I'd like to point out. One, it's not thin anymore. If we look down at it, it's this big round disk. So you can think of our galaxy as like a thin plate. It's not exactly shaped exactly like a plate, but it's pretty much like one. And then on top of that, you have these big, beautiful spiraling arms. So astronomers look at galaxies like this and they say, oh, it has spiraling arms. So we'll call that a spiral galaxy because we're really good at naming things. So we live in a spiral galaxy, which is great. And we have a pretty good understanding of our own Milky Way for having lived in it. We don't understand everything, but we're still studying a lot about it. But one thing we do know is that we are not the only galaxy out there. There are lots of other galaxies. And to prove this point, I have this beautiful image here, which is the Hubble Deep Field. So this is a very famous image, and I'm going to explain why. What they did was a bunch of astronomers in the 1990s got together, and they said, hey, what would happen if we take the Hubble Space Telescope, our most powerful optical telescope, and point it at a black part of the sky? Like, we don't see anything there. Nothing. What would happen if we just point it there for a really long time? And so a bunch of other astronomers who had to approve this plan said, yeah, why not? Go for it. So they spent 10 days and over 100 hours staring at this part of the sky that was supposed to be empty. Very small part of the sky, yes, correct. And they got this. And this is a beautiful image because aside from a few stars, which you can tell have these pointy features here, so those are stars in our own galaxy, the Milky Way. We can't go out there and tell them to move, so we just have to leave them in the image. Everything in this image is a galaxy. There are almost 3,000 galaxies in this image. And as you can tell from it, they're all different colors and different shapes. So there are lots of types of galaxies out there. And we are definitely not the only galaxy. So lots of little islands of stars, dust, gas, and dark matter. So I haven't talked much about dwarf galaxies yet. So let's do that. So this again is the artist's depiction of our own Milky Way and what we think it looks like. What happens if we put a dwarf galaxy next to it? Well, it looks approximately like that. Tiny little square up there in the top left. So it's quite small. Dwarf galaxies are about 1/10 to down to about 1/25 the size of a big spiral galaxy like our Milky Way. So they're very small. So the question becomes, why do we care about such tiny galaxies? What's the point of studying them? Well, first off, there are a lot of them nearby us. And so this image, even though a little bit hard to read, it proves that, where we have the Milky Way in the center labeled in yellow. And then we have these two yellow labels here, which are the Andromeda Galaxy and the Triangulum Galaxy. So those galaxies in yellow are our nearest massive neighbors. So they're big galaxies. Everything else here is labeled in light blue, and those are all dwarf galaxies. There are about, last time I checked, 40 dwarf galaxies with a distance to the Milky Way that is smaller than our distance to Andromeda. So 40 dwarf galaxies fit right in here. That's a lot of dwarf galaxies. So we want to understand where they came from, what they're doing, and what we can learn from them. So one thing we can learn from them is star formation. We can learn about star formation and how it happens. So this is an image, not of dwarf galaxy star formation or Milky Way star formation. This is for all galaxies. So we start off with some really dense gas in the center in the red here. And then that dense gas can collapse and form stars. And then those stars live out their lives as either less massive stars or more massive stars, eventually die. But the main point of this image is that you need dense gas to form stars. And that's actually really hard to get in some galaxies. We don't know how gas always gets to these dense enough states. And so we kind of understand how that works in the Milky Way. And I'm going to take a piece of a spiral arm to show you that. And I'm going to blow it up, and we're going to pretend like it's a traffic jam. But in traffic jams and galaxies, you don't have cars and trucks. You have gas and stars. So what happens is the spiral arm comes sweeping through the galaxy, and the gas in the galaxy gets caught up in the spiral arm like a traffic jam. And the gas starts bumping into each other, creating regions of high density because it gets stirred up. And that high-density gas can then collapse and form stars. So that's generally how you get stars in a spiral galaxy. But dwarf galaxies don't have spiral arms. So they don't have this mechanism to kind of stir up their gas and make regions of high density. So we want to understand what causes their gas to get stirred up enough in order to create stars. And if we do that, then we have a more basic understanding of how star formation can happen without the aid of these extra spiral arms. So some galaxies, some dwarf galaxies, are really good at forming stars, and some are really bad. So in these images I've taken, they're combined images where we've taken the stars, the old stars and the new stars, and combined it with images of the gas. So the gas is in red, and the old stars are in green, which you can see a little bit here in DDO 216. And then the new stars are the blue stars. So those are little pops of blue you can see in DDO 216. And notice DDO 216 doesn't have many pops of blue. So it's not very good at forming stars right now. It doesn't have many new stars. Whereas Hera 36 on the right side has this bright white spot here where it's forming a ton of stars. So it's very good at forming stars. And we want to figure out why. Why are these dwarf galaxies so different? What happened to one that didn't happen to the other to make it really good at forming stars or really bad at forming stars? So I keep having this little symbol in the bottom right. And as mentioned earlier, Little Things is the research group that I belong to and I worked with for my dissertation. So Little Things is actually great because it's an acronym. And it's really fun to say out loud at once when you try to read out this acronym. So where did it come from? Well, first, there was a group called Things. Things was a group that studied things nearby us. So they studied the gas in nearby massive galaxies. And that gas is called atomic hydrogen, or H1. So their acronym is the H1 Nearby Galaxy Survey, or the Gas Nearby Galaxy Survey. So that's simple, kind of easy to remember, right? But then Little Things group came along, and they said, hey, we want to do the same thing as Things, but we want to do it with smaller galaxies. So we want to do it with little things. So then they had to come up with an acronym that fit this, of course, like true astronomers. And they got creative, and now you're about to figure out why I don't ever say the full acronym out loud to many people. It is the local irregulars that trace luminosity extremes, the H1 Nearby Galaxy Survey. So just a great example of acronyms in astronomy and how far they can be taken. So what did we do to get this data? Well, we were looking mainly for the gas data, and we took stellar data from other surveys. And we got that gas data from the Very Large Array Telescope. And this is a beautiful picture of only part of that telescope. There are actually 27 of these dishes that belong to this telescope. And they together make one big telescope, which is great because then you can move them closer together to make a small telescope, or you can move them further apart to make a bigger telescope. So this is a beautiful telescope, which I visited. And we get the gas data from there. Here's me sitting on top of one of the dishes at the edge. Very perilous situation. And then just to explain how big they are, here's me way down at the bottom of one on the right side. So these are giant dishes. They're about 25 meters in diameter. So that's how we got our data. We got it from this telescope, the gaseous data. And we tried to understand what can help form stars in most of these galaxies and some other things. But what I was mainly focused on is regulating star formation in dwarf galaxies. So this is a list of just some of the ways you might be able to regulate star formation. It's a long list. You don't need to read it all. We'll go through some of them. But in general, it just gives you an idea of how many different ideas there are out there for forming stars in dwarf galaxies. And we're trying to understand which galaxies might be doing these things. So we're going to focus on these four tonight. And I did mention regulating star formation was my interest, but really I was more interested in how galaxies can form more stars for tonight's talk. So how do we get more of them, not how do we get less of them? So let's start off with our first way. So you can have old stars forming new stars. So how does that work? Well, if we start off with a bunch of stars that have just formed, okay, these are the stars in the center, in gas. So the gas is the orange here. So if these stars just formed, they're giving off a lot of radiation, if there are enough of them. And when they give off all of this radiation, we like to call them stellar winds. That radiation is called a wind. And what that wind or that radiation does is it heats up the surrounding gas. It also starts to push gas away from the stars because it's just radiation pushing away the gas that surrounds it. And as it does it, it creates a snowplow effect in the gas. And remember, we need dense gas to form stars. So eventually, these stars in the center will start to die off, the really big ones, and that radiation will calm down. And so this dense gas, which is kind of like a bubble around these stars now, can start to cool and collapse and form new stars. So that's how you can get new stars created by a bunch of old stars, the snowplow effect in the gas. So that does happen in some dwarf galaxies. We think we see that. And this is an image, again, from Little Things, with galaxy IC 1613, where in red, you have this beautiful gas. And in the center, you notice a bunch of green, and those are our older stars. And those older stars may have pushed out this gas, because you don't see much red on top of the green here, and given it that snowplow effect, where now you see a bunch of blue or younger stars are forming in it. So this is a beautiful nearby example of a galaxy that might be having this snowplow effect, where older stars are forming new stars. So what's our second way we're going to talk about? So let's pump it up a notch. Let's go to gas consumption, so galaxies eating gas. This is a way you can get a lot of star formation all at once. So this is an artist's image of that going on for a more massive galaxy, but it still works for dwarf galaxies and with a lot of gas, but we'll talk about little chunks of gas. So the idea is you have a dwarf galaxy just sitting out there and some gas is nearby. If that gas gets caught in the gravity of your galaxy, it's going to ram into the galaxy, right? Because it wants to go towards the galaxy when it's gravitationally attracted. And so as it comes ramming into the galaxy, it's going to stir up all the gas already inside of the galaxy. And on top of that, It's providing fuel for future star formation because stars form from gas. So you can get a burst of star formation, and then you're on top of that giving it fuel for later star formation. And we think we see that in 7's Wiki 403. So on the left side here, this is our Galaxies, 7's Wiki 403, where I've combined the images of the stars and the gas again. And you noticed a burst of star formation in the center of this one. And then on the right side, I've separated out just the gas in this galaxy. So on the right side, I have in gray contours here, that's the gas that we think belongs to 7's Wiki 403 for the most part. But we found this chunk of gas in orange that is moving differently than the rest of the gas in the galaxy. So since it's moving so very differently from the rest of the gas, we think this is a gas cloud that's coming crashing into the galaxy. So this is an example of where that may be happening, where this gas cloud is crashing into the galaxy, stirring up the gas, and then maybe providing fuel for future star formation. So that's a really cool example of where we think we see that. Now, I keep mentioning all these names of galaxies, IC 1613, DDO 216, 7's Wiki 403. What does that all mean? Well, they're actually not that interesting of an answer. They're catalog names. So for example, 7's Wiki 403, it's Fritz Wiki's 7th catalog, object 403. Not that interesting, right? Well, the reason why I bring that up is because Fritz Wiki is one of my pictorial heroes. And what do I mean by that? Well, he's really good at taking professional photos. So I really believe that he's reached professional photo level experts. So I'm going to be trying to reach this in my future careers, so just keep an eye out. So anyways, what's our third way that we can do this? Well, we can talk about interacting and merging dwarf galaxies. We're here on the left, we have some Zords that are momentarily interacting and then they let go and go off on their own ways. And on the right, we have some Zords that are merging to become a Megazord. Okay, but what does that look like with galaxies? Well, it looks something like this, where this video I'm playing actually depicts massive galaxies, but that's okay, it works for dwarfs again. And the pops of blue that you can kind of see here are stars forming. So as they pass by each other, they're interacting, and you see lots of pops of blue. So lots of new stars forming, because they're stirring up each other's gas gravitationally. But they're caught in each other's gravity. So they're eventually going to merge. And as they merge, you're going to see lots more pops of blue. So as they're merging, they're stirring up each other's gas a lot, creating regions of high gas density, which can then form stars. But there is, as we replay it, I'm going to show you some signatures that astronomers look for when they are looking for these merging and interacting galaxies. So as they interact, they come close to each other, and the galaxy on the right, you're going to see it change shape. And when it changes shape, it actually leaves these curved features behind. And that's because the other galaxy, its gravity, has ripped the stars off the outer edge and created these curved features. So these are what we call tidal tails. So that's something that astronomers look for when they're looking for interacting galaxies. Then, if we want to look for merging galaxies like these two, one thing we can look for is their centers. So these two have very bright centers, very bright cores, we call them. And as they merge, you notice that their bright cores don't merge immediately. They're still visible for a while. So if you see these two separate cores with a bunch of these tidal tails or these pulled out stars, then you know you have a merging galaxy situation. So in Haro 36, this galaxy I showed you earlier that's forming a ton of stars, we think we see that. So here on the left is the image I showed you before of the stars and the gas in red. And the stars here in this bright white part are forming a lot of them. And then on the right side, I've just pulled out the gas image. So this is just the gas in orange here. And you can see going straight up, there's this really thin feature. And we think that's a tidal tail. And then on top of that, it's possible that this galaxy still has those two cores in its gas visible. So it's still settling down, it's still mixing together. So this is a possible example of a merged galaxy. So what's our fourth way that we can get lots more stars and galaxies? Well, that's through ram pressure stripping. So with ram pressure stripping, you have something very dramatic happening to your galaxy. So the space between galaxies is not actually empty. It's full of stuff that galaxies expelled, stuff that galaxies haven't eaten yet. It's just a bunch of stuff out there. And so if you get a galaxy, like the one in the top left corner of this image here, moving really fast through that stuff, its gas is going to be ripped off. It's just going to be ripped straight off. And that's the stripping part of this word, or this phrase. So when astronomers talk about ram pressure stripping, they don't typically talk about forming stars. They talk about the death of the galaxy in terms of forming stars, because you're ripping off all that fuel for star formation, right? But there is a brief moment when this is happening to a galaxy where there's still gas left inside the galaxy, and that gas is being stirred up a lot. And so that gas that's being stirred up will start to form a lot of stars. And so that's its kind of last burst of star formation before it dies. Well, not really dies, but you get the idea. So this is a dramatic picture of that happening here, and a very beautiful one with a massive galaxy that's moving towards the top left of this image, and trailing behind it in this bluish purple color is a lot of its gas that's just being ripped straight out of it. So with dwarf galaxies, we might be seeing that in Markarian 178 here. So this image on the left, again, is our gas in red and our old stars in green with our new stars in blue. So there's a lot of star formation going on in the center of this galaxy. But in this left image, you notice that the red is kind of trailing off to this tip. So that could be the gas that is being left behind by ram pressure stripping if this galaxy is more moving towards the bottom left of this image. So it's just being pulled straight off. Then, on the right here, I've taken two parts of this image. I've taken the old stars, which are in green here, and I've taken the gas, which is in orange. So the old stars are these gray lines here. And you notice that the stars, the old stars, don't have any gas covering them on the bottom left. And that might be because that gas that used to be there has already been ripped off. So this part, which is forming a lot of stars in the middle, is kind of the front of the galaxy that might be running into all of this stuff and being stirred up. So this is a moment in this galaxy's life right before it may stop forming stars. So we've gone through all of these different ways that you can add more stars to your galaxy, dwarf galaxies. But there are plenty more. You can feel free to ask me about them. I've included one extra there, but we definitely don't have time to go through that. So I just wanted to leave you with a few thoughts to take home. First of all, dwarf galaxies are awesome. Second of all, there are a lot of them nearby. Remember that image I showed you at the very beginning with all of those blue labels. Also, star formation in dwarf galaxies can be triggered in a lot of different ways. We didn't even go through probably half of the ideas out there. And then, last but not least, dwarf galaxies can help us better understand star formation in general, because we don't have those big spiral arms helping us out. So we have to figure out new and creative ways to get stars to form in your galaxy. I also wanted to just plug Astronomy on Tap Baltimore, which was mentioned earlier. We have bi-monthly events the last Wednesday of every month. So if you can't get enough astronomy, join us at Decline de Vol down in Hamden. I'm probably saying that name terribly wrong. But DKD, as most people know it. And we sit in a bar and we have astronomers like myself get up and give you talks while you have a nice drink and relax. So it's a really fun setting. I heard they're just adding food to their menu if you want a snack while you listen to astronomy talks. But our next one will be in September 25th. And we have a Facebook group, so you can look us up. Yeah, that's all.
And I believe we have plenty of time for questions. So, all right, we're waiting for the lovely cube so people online can hear us. 1 second. Thomas is making his way down. Right over here.
So my question has to do with black hole formation and dwarf galaxies. I don't even know if any form or not, but if they do, can you speak a little bit about black hole formation?
Yeah, so this used to be a very touchy subject of mine. No, it's good now. The idea that every galaxy has a supermassive black hole is not correct. However, dwarf galaxies can certainly form black holes. There's a lot of recent research into going into trying to see how many of them have what's called intermediate mass black holes. So a supermassive black hole, I think, is about 1 million times the mass of our sun. But an intermediate mass black hole can be anywhere from 100 times the mass of our sun to about 1 million. And they're trying to figure that out because we believe that dwarf galaxies can merge, or used to in the past merge together to become bigger galaxies. Something like dwarf galaxies used to do that. And so they want to see if they have themselves these seeds of black holes to create a bigger supermassive black hole. And there is some evidence for it, but it's very recent research, so I can't speak too much to the details of it.
What causes galaxies to move? Like propelled or something like that?
Do you mean move in themselves or move amongst each other?
Just moving, like they're crashing into each other and they're disappearing from one another. And
Yeah, so that
creating
momentum comes from when they were forming. So there's lots of reasons actually. So for example, if there's a big cluster of galaxies, their gravity amongst each other causes them to move around each other. And when they were forming, maybe that gas that they formed from and the dark matter that they were formed from may have been moving also. So that all has to do with where they formed and how fast the stuff that they formed from was moving. And also the expansion of the universe, but that's an extra step. We'll pass it down.
Question about the age of dwarf galaxies. Are they generally younger, older than regular
Actually,
size?
a very good question. So people used to think that a lot of, there was a subset of dwarf galaxies called blue compact dwarf galaxies that were very young. And the reason they used to think that was because all we could see were their bright young stars because they had so many of them. But eventually we found out they had this older stellar population that was just hiding behind these young stars. So we think dwarf galaxies generally tend to be older, about, as old as other galaxies. But there are a few galaxies that are young in the sense that they may be going through their first burst of star formation. So in that sense, they're kind of young, that they're just going through this first burst.
And do you see dwarf galaxies mostly in the vicinity? The further out you look, do you still see the same frequency of them?
So it's actually hard to see them further out. So we can see them pretty far out, but if you're talking cosmological distances, which I do have some friends that work in that, we can't see them because they become too faint. They're too dim.
We have a quick question online. Which anime is your animation from?
Oh, I thought everyone knew. This is Cowboy Bebop.
Cowboy Bebop.
Yeah, from the mushroom episode. Yeah.
That's Edward and Einstein.
Yeah, Ein. Edward and Ein.
You didn't mention the Magellanic Clouds. Are they considered dwarfs or?
Some people consider them dwarfs. I mean, they're dwarf-like. They're a little big, but they are dwarf, within the limits of dwarf-like sizes, yeah.
So everything you talked about here would apply? Or-
Yeah, the Magellanic Clouds are a special case because they actually were in one of my images here, which
okay, I
is why
missed
I
that.
said most of the light. So the Magellanic Clouds are these two dots of light down here. They're a special case because they're interacting with each other and the Milky Way. So that interaction part of my talk does still work with them. But it is a very complicated case because you have not only the Milky Way's gravity, but each other's gravity pulling on them.
Thanks.
I have a question about one of those last images you showed of some RAM stripping going on. And there's a portion of it with the light being green. And
Yeah.
what is that green area there?
So this green area is the older stars that I mentioned before. So the older stars are not covered by the red part here, which is the gas, which is why you can see them so well, because that gas has been stripped away from them.
And what sort of gas is that? Is that like hydrogen or is it a
That's atomic
plasma?
hydrogen. It's atomic hydrogen. Yeah. It's the most common element in the universe, so that's why we try to look at it.
Dwarf galaxies have masses comparable to globular clusters. Globular clusters are equally old, but they're all uniformly shaped. They're all spherical. All these galaxies are irregular shaped. Why?
Why are the galaxies irregular shaped?
Yes,
They don't have the gravity to hold a regular
but
shape.
they do. They have the same mass as a globular cluster, which is regularly shaped.
Well, I'm not quite sure how globular clusters form, but my understanding is they've been through quite a lot of gravitational interaction, which tends to form those more ball-like shapes that you see in globular clusters. Whereas these guys, since they're their own entities, if they were interacting a lot with other galaxies, they might form that same type of ball or football shape, which is called an elliptical dwarf galaxy. It's another type of galaxy.
This green and blue, are there false colors?
Yes.
Okay. So I have the others. There's been no reason to introduce any complexity between the dark matter and the visible matter. You just assume it always goes along exactly with. So when you have collision, has there been any work on showing that there is no complexity, or just do you have to assume no complexity?
It's for the dark matter.
Yeah.
So the dark matter, in my work, I just assume it's there kind of doing its thing. But we do actually have Little Things members that work on the dark matter specifically, and the shape of the dark matter, and where it sits. And that is very model dependent. So there's still some ongoing work with dwarf galaxies in general, trying to understand what their dark matter looks like, and how the galaxies might sit in that potential well, that gravity of the dark matter.
We have another question online. What is the age of the Milky Way?
Old. I don't know. Very old.
Can you go back to the Milky Way galaxy, Earth looking in, and then to the conceptual overview?
This one.
Both of those two. I know it's a good educated guess that science thinks that's what our galaxy looks like, but when we look at the previous picture, what data are they working on or collecting to guess that it looks like a barred spiral with, maybe 4 arms?
So there's actually a lot of data that goes into it. Most recent work is with the Gaia survey. So they're actually trying to figure out exactly where stars are placed in our galaxy by measuring their distances. And that's a lot of work, and it's very ongoing. But there are also other types of measurements to measure the location of our spiral arms. For example, in my undergraduate, I did some research with a professor who took background objects, so pulsars in our case, and we measured how their light rotated. And this is a very complicated concept, which I could do an entire talk on by itself. But essentially, you measure the polarization. So you know how your sunglasses are polarized? If you take two sunglasses that are polarized and you put them next to each other, they'll block out all the light. So that's a linear polarization, up and down. So if you try and measure how that polarization changes, you can figure out how much stuff is between you and that light. And sorry, this is like not the most satisfactory explanation, I'm sure, but it's called, it's the rotation of the polarization, and what it does is tells you how much stuff is there, so you can measure exactly where you think the spiral arms are in your galaxy. And it's a very complicated process.
So through that, you were able to predict what's on the other side of
Well, they were able to, from where that thing is, they were able to figure out what's between that thing that we're looking at, the background source, and us. So they're able to figure out how much stuff is in between there. Yeah.
In looking at the dwarf galaxies, how does the typical one compare in size to the Milky Way galaxy?
How does the which one?
The dwarf galaxies, how much smaller would they be than the Milky Way?
Yeah, so I put up one next to each other here. So they're typically, this dwarf galaxy here is one that I showed later on in my talk. It's Markarian 178, the one that's possibly being ram pressure stripped. And they're typically considered to be about 1/25th the size of our Milky Way, all the way up to 1/10th the size of our Milky Way.
Thank you.
Mm-hmm.
We have a question online. Can you recommend some literature about ram pressure stripped galaxies?
Oh, some literature. So I must say I mostly read journal articles, and that is not literature that most people want to read.
I will say actually that recently, just a few months ago, we put out an article on webtelescope.org talking about how the James Webb Space Telescope will look at these exact systems. So for the person online, if you want to go to webtelescope.org, search ram pressure stripped galaxies, that will lead you into a whole cornucopia of literature, I believe.
I also need to read that. Anyone else? You can feel free to ask me questions afterwards, too.
So I remember from decades ago that somebody thought that the sun was between arms, and you now know from this picture I can see that we're on an arm, on Orion's spur.
I think we're close to an arm, the Orion spur. I don't know if we're exactly on it. I would have to look up that article.
Thank you.
We hear regularly about how hard it is to get time on Hubble and time on... How hard was the Very Large Array, which I know is looking for other things, for you to get time on when you were there?
So definitely not as hard as Hubble. Tried that. So the VLA, so it's not easy to get time on the VLA. This is a beautiful picture of it that I showed earlier on, but this is actually the VLA. So it is still difficult to get time on it, and the reason being, especially because they just upgraded it, so they made it a little bit better, and that everyone now wants to use it because it's this big, better machine. But I don't know how oversubscribed it is. I'd have to look up those numbers for you. But I have tried Hubble time, and I find that's a lot harder to get.
Thank you.
second one. In general, could we get an update on James Webb Space Telescope? And Alex?
Yes.
If you've got that, let me know.
Yes, happy to do so. That's actually why I'm all dressed up today, is because we had folks from NASA headquarters come visit us, and we had to brief them on what we're doing. So the latest with the James Webb is that, as I think it was today, there was a successful deployment of the secondary mirror. So they, both the pieces of James Webb, you can look at the model over there, it's kind of turned on its side, but there's the top part, which is the optical element, which has all of the mirrors that gather the light and all of the instruments that analyze the light. And then you have the bottom part, which is the sun shield, blocking the sun and all of its infrared radiation, and the spacecraft. And so currently both of those are two big pieces. They're sitting in California at the Northrop Grumman facility. And they just did a test where they're not together yet, but they're talking to each other. And so they just did a test where they deployed successfully the secondary mirror and got everything working and weightless and all that stuff. Between you and me, in the next, are we still recording? Maybe I should be more discreet. We are in the process of integrating the two halves of the observatory. So sometime in the next few weeks, we will be mating the top half and the bottom half of the observatory. That is the final integration step for the observatory. Then it actually takes several weeks to connect all those wires and make the big thing and the big thing work nicely together. That's happening over the next month or two. I think they actually touch down sometime in the next week or two. And then they'll be connecting all the wires. Everything should be all set. And then later in the fall, they put it all through the whole testing rigmarole, a vacuum chamber and acoustic testing again. And we are still set for a March 2021 launch date. That was my meeting today from French Guiana. And if there's any other specific questions, I'm happy to answer them, but that's where James Webb is right now.
We only get one shot at this one, so we're making sure that it's right the first time.
I have two questions for you. The first one is, are there any particular interactions between galaxies like our own and these dwarf galaxies? Like, for instance, do galaxies like ours break up into small galaxies, or do they merge and become galaxies like ours, or are they totally independent?
So there's many parts to that question, it's a very good question. So at the beginning of the universe, when galaxies were just forming, we think that dwarf-like galaxies existed, and they combined to make larger galaxies like our own. Now, there are still a lot of dwarfs left over. They didn't all combine into these, and they may have formed later, etc. Now, that the Milky Way galaxy also has a ton of dwarf galaxies around it. And so eventually it'll eat those galaxies, and it's currently in the process of eating several galaxies. One galaxy that I can think of is the nearest galaxy to us, which is 25,000 light years to Earth, and it is the Canis Major dwarf. And that is just being torn apart by the Milky Way. And it's possible, well, I'm not quite sure where the research is on this, but that galaxy may have left 3 rings around the Milky Way from going around it 3 times. So it's just being torn apart by the Milky Way, and it eventually will merge with it and make the Milky Way more massive. Does that answer your question?
Yes, it does. But the other question I have is this, in comparison of large galaxies and small galaxies. If you take the aggregate of the dwarf galaxies that are within our region, you said that you can only see but so far away and see dwarf galaxies, but if you take that region that you can see, how many stars might be in dwarf galaxies and how many would be in large galaxies like our own? Are 10% of them only in dwarf galaxies, or do they make up more, 50% of all the
I don't
stars
know.
out
I
there?
would have to look that up. That's a really good question. I have not done that math yet. because I would have to figure out how many galaxies we know of nearby and then figure out their approximate masses and then add them up. I would have to look that up.
Do you have a feeling for whether they have a significant number of stars?
I mean, I don't know.
comparison?
Yeah, I have no idea.
So is anybody studying the formation of solar systems within the dwarf galaxies?
We do not have the technology, as far as I know, to go out that far because Kepler can only see so far out. So we're mainly looking in our own galaxy for solar systems, the Milky Way.
We can barely study them in our own galaxy. I studied protoplanetary disks, planet formation.
Maybe Magellanic clouds with some sort of...
Only in our galaxy.
Okay,
Yeah, and only within several hundred light years.
How far off is the technology to look at other galaxies?
For Kepler, like
Or just-
solar
just-
systems?
Yeah, just anything that's in other galaxies.
Well, we can see the stars in them and we can see the gas, but in terms of Kepler, I would assume we're pretty far off by the sounds of it. So looking at solar systems and other galaxies, we're quite far off.
Any other questions for our speaker? All right, well, let's give her a huge round of applause. Thank you, Dr. Ashley, and thank you all for coming. We appreciate your support. Very glad you're so invested in astronomy, as are we. And again, if you are interested in going on the observatory tour, in a few minutes, just meet up here, and you will be guided by Eleni from Johns Hopkins. Thank you. Have a good evening.